A model can be 99% accurate and still completely fail. For example, let's say you have a fraud detection dataset with 10,000 transactions, and only 100 of these transactions are fraud. Now, suppose the model predicts not fraud every single time. It gets 9,900 transactions right, and that is 99% accuracy, but it catches zero fraud. That is class imbalance. When the outcome you care about is rare, accuracy can make a bad model look excellent. And in production, that is dangerous because the model may ignore the exact cases the business needed it to find. In this video, we'll show which metric should be used to assess performance of a model when you have class imbalance. Welcome to Scovia, where we make AI concepts feel like everyday ideas. Let's look at the data visually. Each dot is one transaction. The gray dots are legitimate transactions and the red dots are fraud. And notice the imbalance. The fraud cases are not just a little less common, they're almost invisible compared to the normal transactions. In machine learning, the common category is called the majority class, and the rare category is called a minority class. But in real business problems, the minority class is often the whole reason the model exists, like fraud, defects, security incidents, urgent support tickets, customers who are likely to churn, etc. These events may be rare, but they're expensive to miss. So the challenge is not just training the model. The challenge is measuring whether the model is finding the rare cases instead of simply getting rewarded for predicting the common case. Because when normal behavior dominates the data, a model can look accurate by playing it safe. And playing it safe usually means predicting the majority class. Accuracy simply measures how many predictions were correct overall. So when one class dominates the dataset, the class dominates the score. A model can predict the majority class every time and still appear highly accurate. So we need a different question. Of the rare cases that actually happened, how many did the model catch? This is where recall becomes important. Recall does not ask how often was the model right overall. It asks of all the real fraud cases, how many did the model find? In our example, there are 100 actual fraud cases, but the model predicted not fraud for all of them. So it caught 0 out of 100 fraud cases. That means the recall for fraud is 0%. And now the model no longer looks impressive. Accuracy said the model was 99% correct, and recall says the model caught none of the things we cared about. That is why recall is often critical in imbalanced problems. If you're detecting fraud, disease, defects, intrusions, and things like that, you usually care about how many of the real positive cases your model is actually finding. A high recall model catches more of the rare cases. But there is a trade-off. If the model becomes too aggressive, it may start flagging too many normal transactions as fraud. That brings us to the next metric, precision. Precision asks a different question. When the model predicts fraud, how often is it actually right? So recall is about what the model finds, and precision is about whether the model's alerts are trustworthy. In real systems, you usually need both. A fraud team does not want a model that misses every fraud case. But they also do not want a model that flags thousands of legitimate customers for no reason. So class imbalance is not solved by chasing one perfect metric. It is about choosing the metric that matches the cost of being wrong. If missing a fraud case is expensive, you may prioritize recall. If false alarms are expensive, you may care more about precision. And if you need a balance between the two, you may look at the F1 score, which combines precision and recall into one number. But the key idea is simple. When the important cases are rare, accuracy is too broad. You need metrics that focus directly on the minority class because you want to measure whether the model is catching the cases that matter. So, before trusting a high accuracy score, ask three questions. First, what is the minority class? Second, is that minority class the outcome we actually care about? Third, what is more expensive, missing it or raising a false alarm? If missing a rare case is expensive, look closely at recall. If false alarms are expensive, look closely at precision. If you need a balance, use the F1 score. And in many real world systems, you should also inspect the confusion matrix, but it shows because it shows exactly where the model is making mistakes. A good model is the one that performs well on the decision that actually matters. I hope you found this video useful. Please subscribe to Scovia and as always, stay curious.